Okay, so good evening, everyone. So, welcome to today's class. This is, I guess, 11th lecture of week 10. Um, so, a few announcements to start as usual. Use the discussion board if you have any questions regarding either of the, many of the topics that we've discussed in the lectures. Give feedback on the lecture after the class. And assignment Q was due today, so I hope everybody was able to do a submission in time. Did anybody not submit yet? Okay, so it will be graded in a couple of weeks, which may be after your exam. So we'll see if we can do it before, but um, yeah. And so I guess the next milestones, there are two. First is the project. So there's a presentation which is going to happen during the class on April 26th. So I'll tell you more details on the format of the presentation and so on in the subsequent lectures. A couple of students are presenting in the student research forum, so try to attend if possible. So you'll get an idea of how student projects should look like. So your course project should at least be benchmarked on the same level as those student projects. And there's also the scope of some of the course projects. They can go as posters or poster presentations in CBA Student Expo. So I'm not fully sure on the logistics of this, but the department holds end of the semester student expo. So some projects can go there as presentations, but this will be right after your exam, so it should be fine. And the final report for the project itself is due on April 28th, so a couple of days after the presentation. So in case you have to do a last minute wrap up of your project, you can do that. So in terms of timeline, we have covered all these topics so far, and today we're gonna spend time trying to review what we've already discussed. Sometimes a little bit of new material, sometimes not. So we're going to look at deep learning, graphical models, and online learning. Next week is the in-class exam, and the remaining couple of topics are related to reinforcement learning. Okay. So the second big milestone that I was referring to earlier is the exam, right? Any questions so far before I talk about the exam logistics? So the exam logistics is as follows. So the exam is on April 5th from 6 to 8:30. It's in this class. I am not sure how many students are actually. So I feel like the number of students in the class is less than the number of students who will show up for the exam. But we will see how to do the logistics on the day. So it covers all the 9 lectures. It's a written exam. So no computation and communication devices allowed. It's a closed book exam, and one basically letter size sheet is allowed, and it amounts to 25% of the grade, and no makeup exams are possible. So any questions about the logistics? Okay. So today we're gonna review some of the topics that will influence your exam preparation. So we're going to go in a slightly different order. We'll first touch probabilistic graphical models because you have recently submitted your assignment too, so you must be more familiar with the topics in that assignment. Then we'll review online machine learning since we only had one lecture to kind of discuss the problem, and then we'll look at deep learning if there is time. Okay. So let's start with probabilistic graphical models. So first we'll just have a warm up. We'll look at a few topics that we've already seen. So these are, and then we'll solve a few questions. Okay, 1 or 2 questions. So let's sample a few key topics. First is conditional independence. Second is Coolidge propagation. Third is I'm going to discuss maximum likelihood estimation again because it's a very important topic that you'll come across maybe in future classes, or you've already come across in other classes. So we're going to tie or review maximum likelihood estimation again. And then we'll quickly touch a couple of applications called naive Bayes and Bayesian regression. I think naive Bayes was already there in your assignment, one of the questions in your assignment. So we'll quickly touch these concepts and then get to some example questions to solve. So in terms of conditional independence, first of all, since there are two types of graphical models in addition to factor graphs, for directed probabilistic graphical models, to understand conditional independence, to infer conditional independence statements from a given graph, there was this idea that we discussed called the deseparation idea. So deseparation relies on paths being blocked or not. So you need to know what graphs are and what paths are on graphs. And then whether a path is blocked or not, there were two types of conditions that you wanted to check. For example, condition on a variable or a set C, whether that set C has a head-to-head structure or some other structure. Okay, so it's basically just verification of the path blocking condition, and you need to ensure that all the paths are blocked between, let's say, two sets A and B, condition on that set C. Okay, if all the paths are blocked, then the two parts are deseparated, and that implies conditional independence of those two sets. So I think we've seen this example before in the class. So yeah, so we are asking the question whether A and B are conditionally independent given C. So we've been given this graph, and we just want to infer whether this statement holds. So you can see that. So we need to check deseparation for all pairs of vertices in the two sets. So A is only just one element, so one node in there, which is x5, and B has two nodes, x4 and x2. So it's easy to see that first of all x2 paired with x5, 2 and 5, they are blocked. The path between those two nodes is blocked by C, right? There is no. It's basically a head-to-tail structure through a single path that exists between those two nodes, and so that's fine. So now we look at the next pair of vertices, which is x4 and x5, and x4 and x5 are not blocked by C. So in aggregate, from these two, you can conclude that they are not deseparated, and so you cannot say that those two sets of random variables are conditionally independent given C. Okay, from the graph, you cannot infer whether they are conditionally independent or not. Okay, is this clear? Okay. For undirected graphical models, the situation was much more straightforward. There were only two types of conditions, so there was no notion of head-to-tail, tail-to-tail, head-to-head structures, or the directions of the arrows were not there, so it made the problem a bit simpler to read off the conditional independence properties from a given graph. So first we looked at the idea of global Markov property, which just says that if you partition the graph into three sets, then if all paths, and you're asking for a question about whether the two sets are conditionally independent given a third set, if all vertices from the first set to the second set, all the vertices on the first set are connected to all the vertices on the second set. If they are connected, those paths only pass through C. Okay, so if that is the case, then they are conditionally independent. And here you can see that if sets 1, 2, and 3, and 5, 6, and 7, for any pair of vertices in this set and this set, the path between them has to pass through node 4, and so those two sets are conditionally independent given the given that node x4. Okay, is this clear? Okay. Yeah.
So, I mean, if I want to infer whether or not x1 is conditionally independent of x4 given x2.
Yeah. Given x2.
That is possible because I have a path from 1 to 4 by 2.
Yes. Yes. Yeah. So. Okay, and next we looked at the second notion, which is a equivalent thing, which is the notion of local Markov property. So here. We are essentially asking whether a node is conditionally independent. So here local Markov property just states that a node is conditionally independent of the rest of the graph given its neighbors. So for any node, for example, x4 is conditionally independent of the rest of the graph given its neighbors, and it has 4 neighbors, 2, 3, 5, and 6. So given 2, 3, 5, and 6, it's conditionally independent of x1 and x7. Similarly, what happened? Oh, x1. Okay, I missed the. Yeah, given x2 and x3, x1 is conditionally independent of x4, 5, and 6. 4, 5, 6, and 7. Okay. So, is this local Markov property clear? What is the? I mean, are you able to understand the difference between global and local Markov properties? So, global is about sets, and local is about a particular node, its neighbors, and the rest of the graph. Okay. Great. So let's look at let's just recollect belief propagation. I assume that since you guys have implemented belief propagation, so you may be a bit familiar with how. So what do these message objects look like? So we'll just step through the 3 key ingredients of belief propagation algorithm. So it has essentially 3 parts. Or 3 types of things that you need to do. First is initialization. You need to start the algorithm from somewhere. Okay, so before that, belief propagation is used to do inference on graphs, and it's exact on tree structured graphical models. Okay, and whether it's directed probabilistic graphical models or undirected probabilistic graphical models, you can convert both of them into a factor graph and then run belief propagation algorithm on the factor graph. So factor graph has 2 types of nodes: variable nodes which correspond to variables and nodes which correspond to factors. So those factors can be, those factors can be arbitrary in undirected probabilistic graphical models, right? Okay, so the thing out of the 3 ingredients, the first thing is to start the algorithm. So you'll start the algorithm at the leaves of the factor graph. Since it's a tree structured graph, there will be bunch of leaves. Okay, and those leaves can be either factor nodes or variable nodes. So if it's a factor node and it's connected to one neighbor, since it's a leaf, it will only be connected to one neighbor. So the first message that so every factor node is as the name denotes, it's associated with a factor in that factorization of the joint distribution. So the first, you start by passing messages from these leaves to their neighbors, and so the message from the factor node to its neighbor is just going to be the factor associated with that node. Okay, so for discrete random variables, it's just going to be a vector. Okay, and it need not be probability mass function. Now, and similarly, if a variable node is a leaf, then it will send a message to a factor, which is going to be a factor node, which is going to be a vector of all ones, for example. Okay, so that's how you're going to start the belief propagation algorithm. Now let's consider a general location. So let's consider that we need to pass a message to a factor node. So we are at a variable node now. Okay, so a variable node will be connected to a bunch of factor nodes, and let's say we want to focus on sending a message to one of the factor nodes. Okay, so this diagram is showing that this particular variable node is connected to 4 factor nodes. So a variable node can be connected to any number of factor nodes, right? As long as it's not a leaf, it will be connected to at least 2 factor nodes, right? So in this example, this variable node is connected to 4 factor nodes, and let's say it's picked one of the factor nodes to which it wants to send a message, right? So what it needs to do is, it's a recursive description of what it needs to do. So it needs to collect all the messages that all the other factors, not its target factor node, but all the other factor nodes have sent it, right? So those are these messages, and of course these messages are going to be indexed by the variable itself. So these are going to be, let's say if this is a binary variable, then this will be a 2-dimensional vector. Okay, all these are going to be 2-dimensional vectors. So it's going to collect all these. So this variable node is going to collect all these messages, multiply them element wise. So for each x, you just multiply these numbers, and then it's just going to pass, and it's going to create a new message, which is going to be the same dimensional vector, and it's going to pass it forward to the target factor node. Okay. Of course, it eventually probably has to do it for every factor node as a target node, but we will see that actually. Yeah, so in a tree structured graph, once you start from leaves, you will see that a variable node in somewhere in the graph will have the appropriate messages already available to it to pass it on to a next factor node. Of course, it depends on how you're gonna, at what nodes you're gonna invoke message passing, but there's a natural ordering of how you're gonna traverse through a tree structured factor graph to pass messages. Okay. And the second variation is when you need to pass messages from a factor node to a variable node. It's very similar to the previous version where we were passing a message from a variable node to a factor node. So a factor node will have a bunch of variable nodes as its neighbors. So as long as it's not a leaf, it will have at least 2 variable nodes as its neighbors. So designate one of them to be the target variable node to which it needs to send a message. Okay. The message length, for example, for discrete random variables, is going to be again the size of the support of the target random variable. So if x is 10 dimensional, it takes 10 values, so there's a PMF associated with it. The marginal is 10 has support on 10 values, then mu is going to be 10 dimensional. Okay. Now the way it's going to create this message that it needs to pass to a particular target node. In this diagram, we are assuming that this factor node has 4 variable nodes as its neighbors. So one of them we have chosen to be the target. So the way it's going to create this message is it's going to collect the messages from the non-target variable nodes, multiply them element-wise. Okay, that's this part of the equation, and then it's going to multiply that vector with the factor that it already has. Okay. With the factor that it already has. Now we need to marginalize all the variables which are not the target variable node. Okay. So for example, this factor is associated with since it's associated with 4 variable nodes. This xf is going to be has 4 arguments. It's essentially x, y1, y2, and y3. So you need to sum over y1, y2, and y3. And then you will get a resultant message which is just going to be a function of x, and that you will pass it to the variable node. Okay.
Professor?
Yeah.
So first we multiply the elements, multiply the messages from other nodes, element by element.
Yeah.
And then we sum it up. Then we multiply it with the factor node.
I mean, you can do this for every x. So it's basically, this equation is for all x. For every fixed x, you just multiply, let's say, 3 numbers here. And then you will have actually for a fixed x, this is a function of 3 other variables, right? So you just sum over all the other variables. So, I mean, you don't need to have a vector point of view, but I'm just saying that for every fixed x, you just need to multiply 3 numbers and then sum over all the other variables.
For every x, as in the state of x.
Yeah. So let's say x is a random variable which takes 10 values, then there will be 10 such computations to create a vector which create a message, output message which is 10 dimensional. Right. Yeah.
For the function x of f, has all y1, all the y1, y2, y3.
Oh, script f, script x, subscript f is going to be y1, y2, y3, and x. Right. If it's a factor associated with 4 variable nodes, then there will be 4 arguments. Yeah. So yeah, basically, so these are the message types that you need to pass around. So we talked about initialization and talked about how to get different types of messages. There are 2 different types of messages. How do you compute actually on a tree structured factor graph is you designate some internal node as a root node, okay, and then you pass messages to the root node in a natural ordering, because you cannot change the order and pass messages. You will see that some messages will not be available if you don't follow a particular natural ordering. And then from the root you can again propagate back all the way to the leaves. Since the root node will now have messages from everybody in its neighbor, so you can pass messages back the way you got the forward messages. So the computation of, for example, marginals. So these, as I said, these messages can, as we discussed in the lecture, these messages can give us a handle on the marginal distributions, for example, right? So a marginal distribution on X is just the product of messages of its neighbors, okay? So computation of marginals for all nodes is just a linear time. One forward pass of messages and one backward pass of messages. Okay. So that's belief propagation. So let's now investigate maximum likelihood estimation. So I think at least one question had maximum likelihood estimation in assignment 2, right? Yeah.
So you were saying that find the marginals for each of the variables is going to be a single pass.
Yeah, you can find marginals. So in any given factor graph, by passing these messages to a designated route and then passing messages back all the way to the leaves, you can compute. So once you pass these messages, every node will have all messages from its neighbors, right? Every node will have all messages from its neighbors. So for variable nodes, you just multiply those messages, you will get the marginal for that.
But what happens is you are designating a node as a root.
Yeah, it's arbitrary.
So only that node will have all the values, so you can only
Yes.
find the marginal of that root.
Yeah, in the forward pass you can only find that, yes. But you also need to, if you want to find marginals of everything else, you can just send messages back as well, right?
From the root node that you have fixed.
Back to all the leaves. Which
all the messages or
no, once the root will have, let's say the root this is the root, okay? It is connected to only 4 variable nodes. We just designated this to be the root. After passing messages from the leaves to this root, there will be incoming messages from all directions, okay? So since there are incoming messages from all directions, you can now send a message from this node to a variable node, okay, which you might not have done before, right? You can do that symmetrically for all directions, and then you go all the way back to leaves. Any questions about belief propagation or conditional independences? Okay, so let's revisit maximum likelihood estimation. So how many of you have already seen maximum likelihood estimation, not just in the assignment but also in some other course? So statistics course typically deal with MLE, right? Okay, so how many of you have not seen maximum likelihood estimation? Okay, so we'll actually go through what. So it's just an optimization problem, right? It has to output something. It has some input. So let's discuss what this is. So okay, so let's say there is a parameter theta which governs the data set that gets generated. Okay, for example, if you're flipping a coin, if the coin is a fair coin, it has a parameter 1/2, right? 1/2 is the parameter of a Bernoulli distribution, and so you flip the coin and you'll generate data, which is in first trial whether it was a head or tails, in the second trial whether it was head or tails, and so on. And so you'll get the sequence of head or tail information, right? So that would be your data, and so you can actually if you assume that one trial is independent from the other, there is no relation between the first coin flip and the next coin flip, and both are driven by the same fair coin, let's say, with bias 1/2, then the probability that you will see a particular sequence of heads and tails is just going to be the product. So here, I guess M just denotes the mth example or the mth trial. It's just a product of the probability of the mth trial leading to some value given the parameter. Okay. And so this is the probability of the data set or the observed data given the parameter, and the likelihood function or the log likelihood function is just the log of the probability of data given parameters. Okay, so I just said let's fix the parameter to be 1/2, but you can just say for an arbitrary parameter what is the probability of seeing heads or what is the probability of seeing tails, right? So for example, so if there was a heads, tails, tails, heads, 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 tails. So let's say this was the data, which is of length 7. Then what is so the question is, what is the probability of seeing this sequence, right? given, let's say theta is equal to something, let's say it's 1/2 or maybe it's 2/3, some biased coin. This is what that is, and since the trials are independent, you can just make it a product, and then you will just have some terms which will be product of probability of heads given theta is equal to 2/3, and there will be some terms which will have probability of tail given theta is equal to 2/3, and so it's just a product of those numbers. Okay. Now, if you write the log likelihood in this way, then the idea of maximum likelihood is to just pick the setting of the parameter. So in the Bernoulli case, when you're flipping a coin, there's only one parameter, which is the bias of the coin. You just have to pick the parameter value that most likely generated the data that we saw. Okay. So different parameter values will assign different numbers or different values to this probability, right? So you just want to pick that particular parameter value which maximizes this probability. Okay. A log is there for some convenience, but you can just see that this is the objective, and I just want to maximize over theta. Okay. And so maximum likelihood estimate is just the argmax over theta of this log likelihood, and it's very commonly used in statistics. A couple of things. Maximum likelihood estimate does not always exist. So even if you can write the conditional probability of the data given the it doesn't have the conditional probability, or if you write the probability of data given parameters and you try to maximize the objective, you may not be able to do that maximization because the objective may be ill-formed, and it may also not be unique. For example, since it's an optimization problem, right? So it could have two maxima, right? It could have a flat line. So if you just imagine how the objective looks like, it may be like this. So every point here is a maximum, let's say, in a one-dimensional optimization problem. Okay. You're optimizing for f of theta, and let's say theta is one-dimensional. Then you can have many solutions which belong to the optimal set. Okay. So let's look at a simple learning problem with one node. So it's a one-node directed probabilistic graphical model, which is what even this example was. In fact, I guess I'm repeating the example. So let x1 to xn be an IID sample drawn from a Bernoulli distribution with parameter theta. Then the log likelihood, the L of I guess I used in the previous slide L of theta comma script b, but you can kind of ignore the script b. So the log likelihood L of theta is going to be the sum of the log of the probabilities of xi given theta over the n data samples, or the n examples that we have seen. Okay, and for each example, you can write the probability of xi given theta as this. Is that clear? So in one way we can write the probability of xi, let's say equal to 1 is theta, and probability of xi is equal to 0 is 1 minus theta, right? Right? But there we have written probability of xi in general. So given theta is just theta to the power xi times 1 minus theta to the power 1 minus xi. Right. So this is an equivalent way to just generalize these two equations. So when xi is 0, then you get rid of this term, you get 1 minus theta, which is the same thing as here. And when xi is 1, you just get rid of this term, you will only keep this term, which is just theta. Okay. So that's what's there in the inner bracket of the log expression. And so that's your log likelihood. Okay. Now the objective is very clear, right? So x is the data, xi's are the data, and theta is the free parameter, and we need to choose this free parameter to maximize this objective function. Okay. So let's do that. So because there's a log and there's a product of a bunch of terms in here, so the log, so we can just split the terms into two parts. Okay. And in the first product, since log of theta to the power xi is just xi log theta. So these are the two terms, right? And you can also see that I'm going to sum all the yeah, so you can just count the number of times xi was 1 and not 1 and just add those two as the coefficients here. Okay, so number of times log theta appears is the number of times xi is 1, and the number of times log 1 minus theta appears is the number of times xi is not equal to 1. Okay, so is this reduction clear what the optimization problem is? That we are trying to choose a theta, and this is just a algebraic manipulation going on. Yeah.
But do we have to like use for different values of theta or
No, so right now we have just said theta to be unknown, and we need to figure out the best theta, right? So you can do. So we haven't come to how to solve this problem. We just said for a generic theta, this is what the likelihood number would be. Log likelihood number would be. This is a scalar, right? So it evaluates to a number given the data, and for any theta, you can evaluate what the number is, right? So once you write this general expression, then you can do your gradient descent and all that. But here there's a simple solution. So is this final expression clear that it's just a function of theta? So data has already been kind of subsumed in n, capital N. I mean, you can evaluate it for theta, right? So you can say theta is 1/2, then what is the likelihood of seeing this data of bunch of ones and zeros? You can evaluate that, right?
so like if theta is getting ahead over
Yeah, here we are assuming a Bernoulli distribution, right? So there is a one scalar parameter theta. It's one-dimensional parameter.
Then to find the proper theta, then you have to do a grid search to find the, let's say you want to find
You
the
can,
parameter,
yeah.
but you do a grid search of all the theta that is possible in the given sample.
Yes, yes. So Bernoulli parameters are going to be constrained between 0 and 1, right? So yeah, you can do a grid search and find all the, for each theta value you can find what is this number and figure out which theta gives you the highest number, and that would be the maximum likelihood estimate of theta given this data. Yeah, that's what maximum likelihood estimation is. It's just an optimization problem where you're searching for theta. Okay, whether you do grid search or even gradient descent or whatever, that depends on how nice the objective is. Okay. Yeah. So I've just written this function is nice, and so Emily exists and is unique. Okay. We'll not go into the details there, but it suffices to just quickly check. So if we want to optimize or maximize the likelihood, so we can do what we know from earlier classes. We can take the gradient with respect to theta and set it to 0. Okay. And if you look at that expression, n log theta plus total number of samples minus capital N. Capital N is some sort of a summary statistic. Okay, it's a technical word used in statistics. Summary stat. So you can just take the gradient, and you can see that the gradient is this, and you can set that to 0 and check that it's equal to 0 at what value of theta. The value of theta is going to be capital N plus small n. Okay, where we define the capital N right there, which is the sum of all the x values. So this is a simple example run through of what would you need to do if you need to do maximum likelihood estimation. And in fact, in most problems, most joint distribution formulations that you will come across, there will be, if it's a parametric distribution, you will have to do some sort of maximum likelihood estimation. Maybe the problem is hard, then you will do some sort of approximation or something else. And in fact, we'll see that one of the examples, I think question 10 in your assignment 2 was actually figuring out the parameters of the particular graphical model when data was missing. Okay, and so you couldn't do the simple straightforward maximum likelihood estimation. You had to do something else, which is the expectation maximization algorithm. So and we'll get to that in a few minutes. Okay. Is this maximum likelihood estimation clear for at least a one-dimensional case? Okay. So now let's look at naive ways. So I think it has many different variations of the what is called the naive Bayes problem. So here I'm just kind of recapping one variant of this. So what is naive Bayes, or what is the naive part of it is that let's say we are trying to classify, given a bunch of words, let's say there are n words, that's the input, and I need to build a classification system that's gonna classify this sequence of words as spam or not spam. Okay, and so the key assumption that this particular system or this particular solution makes is that words are independent of each other given condition on the class or condition on whether it was spam or not, and also the word positions don't matter. Okay, so the word positions don't matter, and the words are independent of each other conditioned on the class. Okay, which is spam or not spam. So think of it as a yeah. As a binary random variable. Okay, so again, similar to the likelihood of the data. So if it was spam, then what is the likelihood of seeing these n words? So let's say we only have n words in our dictionary. Okay, so in this variant of the problem, there are n words in the dictionary, and so the assumption is codified in this product distribution. So we are claiming that this conditional distribution just decomposes as a product of bunch of conditional distributions, simple conditional distributions. Okay, and so if you want to classify given a sequence of words, given whether a word occurred or not, whether that example is spam or not, then by Bayes rule you can see that it's proportional to the probability of spam times this product distribution. Okay, and as we saw in directed probabilistic graphical models, if we have data sets, then we can compute each of these factors very easily by counting and normalizing. Okay, so how does the graph actually look like? This is a binary random variable, okay, spam or let's say ham, and it's connected to a bunch of let's say these are also binary random variables. Let's say we have fixed length dictionary, okay, which only has n words, and these random variables just kind of are either the word exists or doesn't exist. Okay, and so this directed graphical model can be represented in a plate notation, which is this basically just overlapping copies of a bunch of random variables are captured in a square box. Okay, and you can have essentially, I mean, you don't really have to have words, you can have features as well, but let's say we have fixed length dictionary with n words. Then to learn the parameters of this model, you just have to count occurrences of count occurrences of words for each class, basically. So if you have training data, then you will have, let's say you're looking at the probability that the ith word is present, given the class y. Okay, let's fix the class to be spam. Probability that the ith word is present, let's say that represents xi equal to true, is just going to be the co-occurrence of the word and the label being spam divided by the number of spam examples that you have in your data set. Okay, and the probability of spam itself is going to be the number of spams divided by the total data set, right? Actually, this n, think of it as n total, not the number of words in the dictionary. Okay, there is a typo here. So basically, what I'm saying is, for this simple directed probabilistic graphical model, learning is easy. You just have to count and normalize. Okay, given complete data, which is going to be a bunch of words and whether it is spam or not, right? And then your prediction for any given sequence of words is going to be just based on these counts. Okay. Any questions for this naive Bayes classifier? There are other versions, multinomial versions and so on, but this is one simple graphical model. Okay, let's look at a very similar graph again. This is going to be actually just regression. So this is going to be linear regression. So let's say we have data set which is xi yi, and xi is d-dimensional. Uh, it's not very relevant. And let's say the model is going to be linear in the parameter, which is, let's say, w, and we're going to make the parameter a random variable. So in regular ordinary least squares or something, parameter is not a random variable, but here we're going to make the parameter a random variable. That's why it's Bayesian regression. I'm just introducing this function phi, which is irrelevant. Actually, you can just think of it as identity. So it can be just w transpose x, except that now w is a random variable or a random vector. Okay, and the particular generative process or the graphical model that I'm gonna define here is that w is going to be normally distributed with mean can be 0 or something else. If it's 0, then it's a very bad model. But if you have some other, let's say if you have actually a parameter which governs this random variable, then you can learn those parameters. So just like there's a variance parameter, there could also be a mean parameter. I have not given that mean parameter here. And then yi is going to be given wi. It is also drawn from a normal distribution with this as a mean and this as a variance. Okay. And so yi only depends on w. Okay, it doesn't depend on yj. So condition on w is not dependent on yj, but yi is not independent of yj in general. You can't make that statement. Okay. They're tied together by this node w. And these other things are not, we are assuming not random in this model. Okay. So it's a very similar structure to the naive Bayes, but the interpretation is different. Generative processes, you're going to draw a realization of w. You've been given an xi. You're going to compute phi of xi transpose w, add some noise. I mean, with that as a mean, generate a yi, and that's going to be your measurement or dependent variable. Okay. And similarly, I mean, given this, and so given this graphical structure, again, we know how to decompose it by just reading off from the graph, right? It's just a directed probabilistic graphical model. And again, you can use the plate notation where yi's are the n copies. So we'll just put them in a plate notation. And w is called a latent or hidden variable. We have seen that in some examples in the previous two lectures ago, as well as in the assignment. I don't know about the assignment. So w is called a hidden variable, and the variables y's are called observed variables. Okay. So these are just examples of simple graphical models that you may see or you may want to model your data as. Okay. So any questions up to this point? So let's now get into more meatier stuff. So we're going to look at three sample examples, sample problems. First is going to be, we're going to look at the Gibbs Markov Gibbs sampling in a little bit more detail. Okay, and then we'll again revisit assignment to question 10. I don't know how many of you were able to do it successfully, but we'll again look at it in this class, and then we'll step through the EM algorithm for Gaussian mixture models. Okay, so here the twist will be that random variables are continuous, right? So we have only been in, for example, I think majority of the directed probabilistic graphical models we've been seeing are discrete and finite support random variables, right? So we'll look at Gaussian graphical models here. Just a quick question: how many of you have already seen Gaussian graphical models? Gaussian mixture models before? Have not seen at all. Okay, so I guess you have not seen EM as well, hopefully. So we'll look at that later. So Gibbs sampling. So this is a slide from one of, I guess, 2-3 lectures ago, where I was describing Gibbs sampling in the context of inference in graphical models, right? So if we cannot do belief propagation, we'll have to do something else to estimate functions of that joint distribution, right? The function of a joint distribution can be a marginal, can be a conditional distribution, can be an expectation of arbitrary function of those random variables, and so on. So Gibbs sampling is essentially about sampling from a target distribution. In our case, it can be it's going to be the joint distribution, which is characterized by a graphical model such as this. Okay, and the idea is to get samples which are x superscript 0, x superscript 1, and so on. So the superscripts represent indices of the samples. Yeah. Because there is a, I mean, if you write the equivalent factor graph, I don't know if you'll retain the cycle, but yeah, it will give you wrong results. I mean, we can't guarantee that we will get the marginals correctly. I mean, so there's always a baseline, right? You can do exhaustively figure out what is the marginal and so on, but belief propagation on non-pre-structured factor graphs is not guaranteed to converge to the true solutions. Okay. Yeah. So actually, in fact, we don't have to look at directed graphical models such as this. In fact, I could have shown the equivalent factor graph, but in this slide, we will see how to do that. I mean, we'll not see here, but let's just deal with this, and talk about what is called a Markov blanket. So essentially, you can either convert this into a factor graph and not worry about Markov blankets, or you can look at this graph but need to know the notion of Markov blanket. But anyway, so the idea is getting from one sample to the other. So each sample is going to be 6-dimensional. So x0 is going to be 6-dimensional, x1 is going to be 6-dimensional, and so on, right? Those are going to be the samples. Ideally, you want to draw samples from P of x, right? You want to get the six-dimensional vector, bunch of them from P of x, but you can't get that. We'll assume that we can't get those 6-dimensional vectors from P of x efficiently. And so Gibbs sampling idea is about getting those 6-dimensional vectors by updating one variable at a time. So one coordinate at a time. So let's say we start from a sample. So let's say arbitrarily we just chose something in the support of that joint distribution, okay, which is x0. We're going to generate a sample x superscript 1 by updating the 6 coordinates of x0 sequentially, okay, one at a time. So it's and that's the idea of Gibbs sampling. So for example, in this case, you update x4 by conditioning on the rest of the graph, but it happens that conditioning on the Markov blanket of this random variable will be enough, because the rest of the graph is independent of it's conditionally, so x4 is conditionally independent of x1 and x2 given its Markov blanket. And Markov blanket, I don't know if you remember, is just a node's parents, children, and children's other parents. Okay, that's it. That's the Markov blanket. We don't have to actually do that on a directed graph. We could have worked with a factor graph actually, but it's okay. So Gibbs sampling is not very specific to directed or undirected or even factor graphs. So Gibbs sampling is a general procedure of drawing samples from a joint distribution from which you cannot sample directly efficiently. And so let's say the joint distribution looks like this. So it's P of x, and for simplicity, I don't think we need to decompose it as a numerator and denominator. But so the idea is we want to sample from, and this is going to be the idea for general Markov chain sampling methods. And the idea is going to be we're going to define something called a transition probability distribution. Okay, here I'm representing it as q of x to x prime. It just means that I have a sample x. Okay, I have a realized value x, and what is the probability of me getting a different realized value x prime? Okay, it's just a conditional distribution. It's called a transition probability matrix. For example, in Markov chains. If you have seen Markov chains before, but it's just a probability of. So all the written. So Q of x2 x prime is just probability of that that's a 6-dimensional vector is equal to x prime given some okay let's call it so this is the full notation for that conditional distribution. It's just a transition probability value, okay? And so the idea of Markov chain methods for sampling is that you want to create, somehow design this, okay? And git sampling is one such design of the transition probability matrix, okay? You design this, and if there's a transition probability matrix for a Markov chain, there will also be something called a stationary distribution under some nice conditions, okay? So we'll discuss what is a stationary distribution in a couple of slides, but there will be a stationary distribution, okay? And the idea of Markov chain-based methods is to design this transition probability matrix such that the stationary distribution is going to be P of x. Okay? So you want the stationary distribution of a Markov chain to be P of x. That's the high-level idea. So you design this transition probability and ensure that the stationary distribution of this Markov chain is P of x. Then if you can get samples from, so if you can draw from this conditional distribution, you'll still be able to get samples from the stationary distribution after a long enough time. So we'll see that in the next couple of slides. Yeah. So the distribution from which we actually want to sample from is P of x, but we can't sample from that efficiently. And so we're going to use a Markov chain-based sampling method, and for that we need to design an object called the transition probability matrix. Okay, so let's say so these states are going to be these 6-dimensional vectors. For example, in the 2 slides ago we saw an example which had 6 random variables, right? So it's going to be a 6-dimensional vector. So we want to design a transition probability matrix, but before that let's define something called the probability of being in a state x at time t. So x is going to be a 6-dimensional vector. Let's say these are discrete random variables, so each coordinate is a discrete random variable. Let's say it's just binary random variable for simplicity, okay? So if it's a binary random variable, it's going to be 2 to the power 6 states, right? 64 states, and pi of x is going to be a number associated with each of these 64 states. Okay, so I'm calling a realization of the random variable to be a state, and pi of x is just a number. In fact, it's a probability distribution, and it's just the probability of being in state x at time t. So what is time t? Since it's a Markov chain, it has a notion of time or a sequence, right? So a Markov chain has to start from some state. Okay, let's call it x naught. And because of the transition probability matrix, because you're sampling x prime, which is the next state, given the current state, it will go into some other state x1 and so on. So this that's why there's a notion of time, and we're just denoting by pi subscript t. Pi subscript t of x. What is the probability of landing in some state? So this is for all x, right? So whatever number of states, let's say there are 2 to the power 6 states, so for all x in our set of states, okay. So we just describe that probability distribution. Yeah.
How do you actually get that probability distribution? Do you need that to follow this, or
Yeah, you can get that by just recursing, right? So we have the transition probability. So let's say our initial probability is that we are going to start from, let's say, the first state x, some designated realization. Let's say 0, 0, 0, 0, 0, 0. 6 numbers which are zeros. Okay. Then we can find the probability of being in any state by which is just going to be the probability of transitioning to any other state given the current state is 0. So pi 1 of x is just going to be q of x itself, right? So I have pi 1 of x. Now pi 2 of x will be again similarly. So I have some probability of being in some state, and from that state I can transition to x prime with this transition probability, and I'm going to sum over all states from which I can reach the final probability. So this is just the chain rule of probability, right? So it's just probability of theta times probability of guess theta prime when this is what is it? Sorry, it's not. Huh? Yeah. This is going to be This is somehow theta, and okay, I should not have used theta. I should have used x, but the joint probability is summed over one of the random variables. Okay, that's what this is. Okay, let me not use. I am summing over x. So this is just the joint probability, right? Probability of capital X 0 equal to x and capital X1 is equal to x prime. Right? So I'm just marginalizing, and that's what this is. So is the transition equation clear? Yeah.
In this particular, Gibbs sampling, do we assume
We'll get to Gibbs later, because for Gibbs we need to define what is this. We have already defined implicitly, but we'll revisit that transition probability in a slide. But this is for any general Markov chain, right? You start with the initial probability distribution over the states, which can be a discrete distribution which can be a degenerate distribution in the sense that I will start with 0, 0, 0, 0, so there is no probability mass for everybody else, and then pi 1 of t will be just from 0, 0, 0, what is the probability of going to all zeros, what's the probability of going to all zeros but last one, all zeros 1, 1 and so on, right? So that's what I'm trying to define here. So this probability of being in state x at time t. Okay. So basically the interpretation is the probability of you being in time t plus 1 at state x prime is going to be the probability that you were in some state x, okay, in the previous time, okay. What is the probability that you were in some state x in the previous time t, and the probability that from that state you're going to come to this state, okay. So a very interpretable definition. So what are the different ways you can get to state x prime? You can be in any state x, but what is the probability that you're going to be in that state times the probability that you're going to transition to this x prime, okay. The probability that you're going to transition from x to x prime is just this factor, and the probability that you were in some state x in previous time is just pi t of x, sorry. And so you can sum over all the states from which I could have reached x prime, and it can be, if it can be restricted, it can be all states, right? And so the reason why I wanted to introduce this was to bring up the notion of stationary distribution. So a stationary distribution is a distribution where pi t is equal to pi t plus 1. Okay. So there is no variation in the probability of being in a state at time. So probability of being in a state x at time t is the same as probability of being in the state at time t plus 1. Okay. Some sort of equilibrium or steady state has been reached, okay, in that Markov chain. Which one? 2 to the power 6. I just said, since there were six coordinates in that example in the directed probabilistic graphical model, I said let each one of them be binary. So you'll have 2 to the power 6 states. Okay. So for example, the summation can be over 2 to the power 6 numbers, which is not that big. So this is how you would get a stationary distribution if this is true. Okay, if pi t is equal to pi t plus 1. Okay, and
so the condition is that a stationary distribution is the required condition in order to be able to, in order for
Markov chain sampling methods to work, we want the stationary distribution to exist and to be equal to our target distribution, which is p of x. So
the choosing the distribution q,
yeah,
it should be able to reach.
So if you choose something random, first of all, the stationary distribution may not exist, and even if it exists, it may not be p of x. It can be something else, right? So there is some art in choosing this q, and that's where Gibbs sampling and Metropolis Hastings method that I don't know if you saw. Okay, you might have seen in the assignment. So those are all designs of this transition probability matrix. Okay, or transition probability function of the conditional distribution, basically, one-step conditional distribution. Okay. So when do we have the stationary distribution? Let's assume discrete random variables with finite support. In the sense, let's say the binary case that I was talking about, that I've been talking about. There are a couple of conditions. One is something called ergodicity, and the second thing is something called the detailed balance. So these two conditions determine the existence and uniqueness of the stationary distribution. I'm just saying that stationary distribution doesn't exist all the time. So there are a couple of conditions that you can check that you can check hopefully in a long time, but you can check that that are necessary and sufficient for a stationary distribution to exist and be unique. Okay, and so we'll not focus on ergodicity. Let's focus on detailed balance because that's going to be useful for us in trying to understand Gibbs sampling. Okay, because our objective main goal is to understand Gibbs sampling. So what is detailed balance? Detailed balance condition is as follows. So X, if there is a stationary distribution, okay, which let's call it pi of x, okay, then the probability of me being in state x, times the probability that I'll transition to state x prime, this joint probability, right, is going to be equal to the probability of me being in state x prime and transitioning from x prime to x. Okay, it's some sort of a symmetric relation. That the probability of being in x and going to x prime is the same as probability of being in x prime and going to x. Okay, that's just a detailed balance condition that we are defining. Okay, and this has to hold for all x and x prime. And detailed balance implies stationary distribution. Implies that the stationary distribution is this pi. Okay. What is it? Then pi is a stationary distribution is what I'm claiming. I'm not saying that this is enough to say that there exists a stationary distribution. You need the ergodicity and detailed balance are necessary and sufficient. But I'm just saying that if some pi satisfies, so we want to design Q, right? So let's say we design some Q, and there was some pi for which this equation holds. As long as the Q we design ensures ergodicity, that's something else. Ergodicity just means that the Markov chain is aperiodic in the sense there is no cycle in that chain while coming back to the same state. While coming back to the same state, and it's positive recurrent in the sense the mean time to get back to that state is finite. So if those two happen, then it's called ergodic. But anyway, what I'm saying is Q is what we design, and we want to see if some distribution, some distribution pi of x, is that going to be the stationary distribution or not? And if that pi of x actually satisfies this, then it is going to be the stationary distribution. So it's nice verification condition to see which pi, if pi is a stationary distribution or not. Yeah.
Is this a necessary condition or a sufficient condition? Does it have to go to be stationary?
No, it's just sufficient condition. No, this is just we are just verifying, right? If pi satisfies this, then it is the stationary distribution. And of course, with just this condition, you cannot say that something is stationary distribution. As I said, some other conditions need to hold. So it's just sufficient.
So if at all it has to be a stationary distribution, this condition has to hold.
No, this condition and ergodicity will give you that.
This one condition has to hold along with some other conditions as well.
Yeah, which is that. Yeah.
So effectively, stationarity implies detailed balance, not the other way around.
P implies Q means it's a necessary condition or a sufficient condition.
It's the other way around, right? Because if it's stationary, then you say that you can have detailed balance. But as you just said, that if you have only detailed balance, then you cannot say that it's
Yeah. So this is not a precise statement. So okay, don't.
So that's should be Q implies P, right, in this case.
No. Even that is not a precise statement. So all I'm trying to say is that if there is ergodicity and some pi satisfies this equation, then that is the stationary distribution. Okay. So let's say this equation is true. Okay. It's very easy to check. the detailed balance equation implies stationary distribution. Okay, implies phi is a stationary distribution. So first of all, let's recollect what was the definition of stationary distribution. It was this phi of x prime was equal to sum over x of being in some state x and transitioning to x prime, right? If a phi satisfies, it's a equation. In fact, can be linear equation. If a pi exists, it satisfies this, and that's the stationary distribution, right? Now, to see detailed balance implies stationarity, we can just do this operation. Let's go from the right hand side. So let's say sum over x of phi of x times q of x to x prime. So that is the right hand side, and we just know by detailed balance this equals to sum over x of phi of x prime q of x prime to x, right? And this is nothing but phi of x prime times sum over x, the probability of x given x prime. Right? I mean, instead of q, I could have just written the q thing, but I'm just saying q is just a conditional distribution, one-step conditional distribution. And now this is just 1. Because you're summing over all the realizations of the left-hand side argument, right? And so this is what the left-hand side is. So that's nice. So if some distribution pi satisfies, so we created a Q, and if we can ensure that some pi satisfies that, then we're good, right? That pi is actually the stationary distribution. I mean, modulo some other conditions which we'll not check. Okay, that pi exists and is unique and all that. And this is what is written over there, so don't have to copy. Yeah.
So basically, add up to one way, only if the Q distribution is transitive, the distribution is always.
This is always a conditional distribution, so it will always add to 1. It's a distribution, right? It's a transition probability matrix. You don't have to think in terms of matrices. So Q, when I write Q of x prime to x, it's actually probability of x given x prime. So it's actually a conditional distribution. And if you sum over all the arguments to the left of this vertical line, then it should be a distribution, right? It should, for every given x prime, it's just a distribution. Yeah. Any other question? Okay, let's get back to skip sampling, which is the simple idea that we sample each variable in turn given all other variables, right? And we want to and our hope is that the stationary distribution is p of x. Okay, so this actually is encoding our transition probability distribution, or Q. So we saw what Q was, right? So we were gonna go from coordinate to coordinate. So starting from, let's say, xt, we would pick the first coordinate of xt plus 1, condition on all the other variables being fixed and to be same as xt's other coordinates, right? So if you remember, going from x naught, let's say x naught was 6-dimensional. Let's say it was all zeros. To get a sample finally, which was x1, which was something. Okay, I would draw. So I'll start with I'll construct x1. Okay, in 6 steps. Okay, so I'll do x1's first guy as a sample from x. So lower script means coordinate of that, this coordinates of these random variables in the graph. Let's say if there is a graph, or it's just the coordinate of the random joint distribution. Probability of x1 given x2 is equal to 0, x3 is equal to 0, and so on. x6 is equal to 0. And similarly, 2, 1 is probability of x2 given x1 is equal to whatever x1 1 was. I mean, you can use this. Actually, you should use this. Comma x3 is equal to 0 and whatever. So you'll do the 6 steps. So this was the way in which you're generating the next sample, right? So that is implicitly giving you. So this in aggregate is giving you the transition distribution Q. Right. So let's try to show that the P of x is the stationary distribution for given sampling. So I've used this condition on evidence because some random variables might already be observed. So in generality, I'm just saying that condition on the evidence. Let's say we want to sample from this distribution, and this is the way in which we are generating the samples, which implicitly defines the Q. Then we'll be able to sample from. We'll see that this is actually the stationary distribution of that Q. Okay. So okay. So let's say we are sampling xi, okay, and let x bar I be all other non-evidence variables. So let's say a bunch of variables are evident, so we don't care about them, okay, in the sense they are observed. And so the remaining graph, let's focus on one node, and the remaining nodes are x bar I, okay. And let's say the current values. So currently, in the previous sample or whichever step you are in that sequential procedure, let's say current values are small xi and small x bar of I, and E is fixed anyway, evidence. Remaining variables are anyway fixed. Now, the transition probability is given by this equation, which is the probability of U being in xi and U being in this state and going to some state x prime, right? We are sampling the next state x prime, right? So, and that we have just written it as this. Actually, this is what it is. The conditional distribution. So, if you remember those equations that I was writing, it's just probability of what is it? Probability of x prime I given x bar I and evidence. Evidence is just tagging along. It's not very consequential. Okay. So this is a short form notation, but you can think of the random variable equal to this given other random variables equal to these small values, right? Lowercase values. So this is a transition probability function, and we just need to show that phi of x times this thing x prime I given x bar I e is equal to phi of x. Okay, phi of x I, sorry. Yeah, no, pi of x. It's fine. Times probability of xi given x bar. I mean, we're just trying to see, what pi. I mean, this is what I said was the transition probability, right? And we are trying to now bring back the detailed balance equation and say, okay, what is the pi which will satisfy this, right? if you're going to transition from x, so what is this xi? So we transition from xi to x prime of I, right? In the step when we changed one coordinate, the previous value was xi and now we have an x prime I. So yeah. Yeah, so the new value is x prime I. I don't know what I'm trying to say. I'm just saying that, so this is the probability of outflow, right? So probability of being in state x and going to some state x prime, one of the coordinates. And this is the probability of going to being in x prime and going to, and changing one of the coordinate to xi. That's the outflow inflow equation, detail balance equation. And we can actually, so we'll just do verification. We're not going to do much. We're going to just say, okay, if I write phi of x is equal to probability of x given e, and phi of x prime to be whatever probability of x prime. Okay, not x prime. Should I use vector notation? Yeah, no. I mean, I've indexed subscript I to be the coordinate of x prime. So this is fine. So probability of x prime given e. So we want to substitute this. So if probability of x, so forget about the evidence. Evidence is just fixed. We want this to be the stationary distribution, right? This is the detail balance equation. If we can substitute this and check whether the left hand side is equal to right hand side, then we are fine. Then p of x given e or p of x is the stationary distribution of this Markov chain, right? Is that confusing? Yeah. No. Detail balance equation is for, if you remember from the previous slide, it's for all x and x prime. That summation thing was to show that detail balance implies stationarity. So this is the detail balance equation. Okay, so we've done it I will not do it on the board because of time issue. So you can see that, right? So probability of x, let's substitute for pi, we'll write pi of x given e. So that's the first term. We just retain the second term to be the one-step transition that we are doing. So we've frozen all other variables, which are x bar of I, and we're going to transition to some, let's say, fixed state xi prime. Okay. Then you can just decompose the first term. Not decompose, but explicitly write xi and x bar I, right? Because x is actually xi and x bar I. And then you can again write that in chain rule. So you can condition the xi on x bar I and then write down the probability of x bar I, right? And then you use opposite chain rule. So you merge these two and get probability of x bar I, comma x bar. Xi prime, comma x bar I. So you just merge these two terms. And if you merge those two terms, that is pi of x prime in that step, right? And this is just a transition probability of going from going to xi. Going to x and x's ith coordinate is xi. So there's not much happening there. There are only two steps. Just algebra. So, any questions about verifying that Gibbs distribution, stationary distribution? Gibbs sampling stationary distribution is actually the distribution of interest, which is p of x. So x prime and x just differ on one state, which is xith coordinate. X, the boldface x there, we are only focusing on the ith coordinate and changing that to xi prime. That's all. So x, so these two just differ by one coordinate being different. That one coordinate is either xi or it's either xi prime. That's all. So for those two fixed states, we are just checking the detail balance equation here. There's nothing else happening. Okay. Yeah.
So here what you're trying to say is, if you use Gibbs sampling, you'll be able to come up with a distribution Q which satisfies a station.
No, Gibbs sampling already implies that transition distribution, right? When I did Gibbs sampling, I was saying freeze all other variables, just sample one of them, fix that, and sample another variable, freeze everything else. So there was a sequence of steps that we were doing, right, in Gibbs sampling. Sample each variable in turn, given all other variables. That implicitly defines the Q function. Now for that Q function, we want to say that the true distribution of interest, the target distribution P of x, is the stationary distribution.
Why do you say that the probability of going from one state to the other state is the same as the other way around? Then it's stationary, right? That's what this is saying.
No, we defined a condition called the detail balance, where probability of being in state x and going to another state x prime is equal to the probability of being in that other state and coming to this state.
So we can extend it, right? Why do we have it to only 2? We can have 3 states and we can go from A to B, B to C, C to A that way.
I mean, 2 states is enough to claim that whatever marginal distribution, whatever pi of x satisfies this 2-state relation is the stationary distribution.
Could
Why
we
do
also
you need-
extend it?
You
It
could,
may not be
you
necessary
could.
that A goes to B and B goes to A. B can go to C also, C can go to A. Or we can make similar.
No, here we are assuming you can go to x prime from x. I mean, for all states x and x prime that are actually, yeah, it has to be. So those types of, I guess, third order relationships may be needed if there is no path from x to x prime. There's no direct path from x to x prime, maybe. Like there's no way to transition from x to x prime.
If it's directed. I can
No,
go
no,
from 1 to 2 to 1. That's all.
No, I don't understand your question. So we have a relation between 2 states, and we said the relation between 2 states implies the stationary distribution. Now your question is?
My question is now, you're saying that I'm equally likely to go from 1 to 2, and I'm equally likely to go from 2 to 1. Like if
When I'm in stationary.
Yeah,
when
so
I'm at,
what I'm saying is that if you're in 1, you can go to 2.
Yeah.
Let's say that if you're in 2, you can go to 3, and if you're in 3, you can go to 1. This will also be stable, right? Because
yeah, you can write some equation like that, but I'm not sure if that equation is a sufficient condition for stationary distribution. Oh. I mean, whatever pi of x appears in that cyclic relation is the stationary distribution. I don't know if that is sufficient. You can show that maybe, but this is enough. Relation between 2 states is enough to claim that this argument that is appearing in that equation is the stationary distribution. But you can go to any higher order transitioning system of equations. Okay, so let's actually go to assignment 2, question 10, which was expectation maximization for a directed probabilistic graphical model with incomplete data, right? So just to recollect what that question was. So who is not familiar with this question? How is that possible?
group work.
Okay. So actually group work implies that you collaborate and work on every problem. Okay. So this is actually very practically relevant problem, right? So here we are saying, let's say we have a very simple directed probabilistic graphical model with 3 random variables. Okay, and in fact they are just binary random variables, and we have observed data from their realizations. Okay, so we have 7 examples, which are as follows. Okay, and it so happened that we couldn't read the measurement of the first random variable A in the 4th example, and second random variable B in the 7th example. Okay, so those numbers are missing at random. Okay, in a sense, there's no relation to them missing at that their position. There is no relation between them missing and the value of the random variable. Okay, that's what missing at random just means. Okay, And first question was estimate the initial parameters of the network using maximum likelihood estimation. And the second part was we wanted to show calculations by hand for 2 iterations of what is called the expectation maximization algorithm for this problem. Okay, and so what that means is there are 2 steps in this particular algorithm as detailed here. So EM, we'll get to EM in a bit more detail again. So EM is all about filling in the missing values, that is Z1 and Z2 somehow, and then estimating the parameters of this directed probabilistic graphical, this joint distribution, and then using that joint distribution to again estimate the missing entries, and again using those estimated missing entries to again update the parameters of the joint distribution. Okay, so let's do the MLE and then take a quick break. So we are asked to use MLE. So the graph is this, and because the graph is like this, this is going to be the decomposition of the factors or the decomposition of the conditional distributions, right? Terms. And parameters theta 1, theta 2, theta 3 need not be scalar yet. So we'll see what those parameters are. And so they specify the conditional probability tables of each of these terms, right? These are 2 conditional probability. They will be characterized by 2 conditional probability tables, right? And so we'll compute this theta 1 MLE or ML and theta 2 and theta 3 now, and show that these estimates can also be obtained by counting and normalizing. So somebody had raised a question about counting and normalizing versus doing maximum likelihood estimation. So in this case, you will see that counting and normalizing is the same as doing MLE, and we saw that even in the naive Bayes example, right? Or even in the Bernoulli example, it is just counting the number of positive or ones divided by the total observations. So out of the 7 rows, 2 rows have missing values. So we are told they are missing at random. So first thing we can do is we can ignore the 2 rows with missing values. Okay, so that's one way to address the first part of the question. But there are other ways to address the first part. So I don't know if somebody else has done it in a slightly different way. It's fine. But one way is to ignore the 2 missing rows and then do maximum likelihood estimation on the remaining. Now consider the case where in every row you had some missing random variables. Okay, you had 100 columns, and in every row there was something missing. Now you can't ignore all the rows and do MLE, right? So you'll have to do something different there. But it's not very different than what we'll do. So we'll not go into that version of the problem. So let's write the log likelihood function, which is a function of the 3 parameters. Which is going to be, I just wrote down the joint distribution of probability of A, comma B, comma C, right? The joint distribution that we saw. Because of the graph, it decomposes into 3 terms, and I've just written those 3 terms. And because it's a log likelihood, there is a summation over the 5 entries of the table rather than a product. But this is the decomposition. And after the break, we'll see how to maximize for the 3 parameters of this function. So it's very similar to the Bernoulli case that we saw earlier. Okay, so let's pause for a couple of minutes and get back.
Just a quick question on that one. So actually, I actually use count. I actually use count and normalize some kind of like.
Count and normalize? Yeah.
Yeah.
It's the same as this.
Okay. Yeah.
That's what I'll show.
Yeah, that's why I actually like try to compare the 2 different methods. Yeah, they kind of like try to.
Oh, they are not supposed to be different.
Oh no, I mean, so for the MLE you carry it this way. Are you like completely ignore that row or just that value?
Oh, okay. You can. So I'm assuming that we can ignore the row. Yeah, if you just ignore the value, that's also fine.
Okay.
That's also fine. Yeah,
So
that's why I said.
So basically,
just
you are
one way
saying
to
like eventually they will produce the same result.
Yeah, of course, the first answer will be slightly different, but then eventually you will produce the same result.
One comment first. So we submitted the first 9 questions, and then we submitted the 10th one like at 6 o'clock. Is
Okay.
that okay? I emailed you guys.
Should be fine. Did you email the TA?
Yeah. I
Okay, then it
CC'd
should be
it.
fine.
And second thing, are you gonna like talk about any like just like I need like just give a direction onto what type of questions to expect.
Yes,
Because if
yes.
it's anything like
Because this is a
the
question,
actual
right?
assignment,
Yeah.
we don't have 3 days.
Okay.
I mean,
No, it will be
just
much
like-
simpler versions of what we're discussing.
Okay.
It's not supposed. Yeah.
Like so, for example, we're talking about gift sampling and all that. Do we need to know exactly how to do detail balancing and
you need to know what detail balancing means.
Yeah, I understand the
We are just
conditions.
verifying things, right? So
Okay,
we're not
right,
even
right.
proving things. Actually, we'll prove something at the end. But it should not.
Every day.
The level of the exam would be much simpler than the assignments.
Okay, and like,
Has to
are
be.
you gonna talk about like everything we need, like
Topics?
like MCQs? I heard it was the first 9, everything.
I mean, we have not yet decided the
Okay.
full
Are you gonna
paper
like
yet.
just?
There will be true, false and stuff. Yeah, it should be easy. It should not be
You
difficult.
say that. You said that this was gonna take very little time. 12 days. I did nothing but this assignment. Look at my face.
Okay.
This is not simple.
No, I
Half the
really.
people don't know what this question is.
Oh, really?
Thank you, though.
Okay.
In the exam, will there be numericals or like these
Will
derivations or
play
something?
good portion will be numbers,
Numbers?
not derivations. I think. We'll decide.
Okay.
We'll decide based on the assignment 2. I have not seen anybody's solution yet.
Okay.
Yeah.
Thank you.
Okay, so we're going to resume. Okay, so we're going to resume, and the state of affairs was that we said for the first problem we have to do maximum likelihood estimation. We don't have to do maximum likelihood estimation. We can just do count and normalizing, and we'll see that they are the same answers. Okay. So from the table we said let's first ignore the 2 rows with missing values. You don't have to do that. You can do something else as well. But let's ignore that, and now we have full data. Right, and we have a graphical model. We have full data in the sense every row has everything observed, and we said okay, let's maximize the likelihood of this joint distribution. So because we have the graphical model, our joint distribution decomposes in this way. Okay, and we've taken the log factor there, and that's why there's a summation over the 5 examples in our table, right? And to write it more explicitly, we'll do the first simplification, which is log of a bunch of products. So a bunch of product terms is just the sum of the logs, right? So we'll split the this single term into 3 terms, okay? And so I'm propagating sum to all the 3, okay? And so now you can see that each term involves its own specific optimization parameter, so optimization variable. So we are trying to optimize over theta 1, theta 2, and theta 3. These are objects which are which parameterize these this joint distribution. But you can see that each term is specific to a particular parameter set. Let's say we don't know whether it's a single parameter or not. We'll see that. So the first simplification is that we split the problem in 3 problems. Okay, because the first. So this parameter is only influencing the first term. It's not influencing. It's constant. Is not influencing the second or third term. Similarly, the theta 2 MLE is not influencing the first and the third terms, and similarly theta 3 MLE is not influencing the first and second terms. Right? Is this clear? We just use the structure of the graph to split our joint distribution into 3 parts. Right? Given any parameter. And by just doing some algebra, we notice that there are 3 terms and each term is specific to to its own parameter set, right? Is all the 3 steps clear in this slide? Yeah.
So is this just like variable elimination?
No, this is learning, right? So we are trying to optimize functions. So it's like similar to what you're doing in the first part of the course, where you're optimizing the cross entropy function and so on. So variable elimination is for a completely different purpose, which is for inference. Here we are trying to learn the parameters of the joint distribution itself. Like learning the parameter of the Bernoulli distribution was a maximum likelihood estimation problem, right? So that was not variable elimination. There you are trying to find the bias of the coin or something like that. So here we're trying to find the parameters which govern this probability, this conditional probability, and this conditional probability. Parameters are just numbers in that conditional probability table, and we'll see that table soon. Yeah. Any other question? Yeah, all I've done is so the number of examples was 5 because we eliminated 2 rows, and we said because let's associate a parameter with each of these terms, and since other terms don't depend on this parameter, so we can have 3 different simpler optimization problems, right? So is this clear? So the optimization over theta 1 just depends on the term which involves theta 1. It doesn't involve other terms, right? So I've broken down this optimization over 3 sets of parameters into 3 problems, okay, where I'm optimizing each individual parameter separately. That's clear, right? Okay, so let's now do the maximization. So the first maximization is as follows. So let's so this is the objective of this problem, and let's say, and so what is this little ai? Is the realization of the random variable ai. So it can be true or it can be false. So let's say probability of a is equal to true is theta 1, okay, and then the probability of a is equal to false is going to be 1 minus theta 1, right? It's just a binary random variable a. And if you substitute that, so there were, if you look at the table, there were, I guess, 2 trues and 3 false values, right? So this summation is just decomposed into 2 log of what is this value when a is true is theta 1, and 3 times log of what is this value when a is false is 1 minus theta 1. That's what happened. In fact, what we are doing in this slide is actually the same as what we saw in the Bernoulli maximum likelihood case a few slides ago, right? And so for this optimization problem, you only have one scalar parameter theta 1, and so to optimize that, you can actually just differentiate the objective with respect to theta 1, set it to equal to 0, and get a value for theta 1. Okay, in a sense, there will be some theta 1 which is at the critical point. Okay. Okay, and then ideally you also want to check the second derivative and show that it is negative, implying that theta 1 star is the local maximum. Okay, and so since it's a local maximum, it's not necessary that we have to show that it is also a global maximum, but since it's a local maximum, we can just call that the MLE. Okay. So our theta 1 MLE is just 2 by 5, and this is for random variable a. It is just the same as the Bernoulli coin flipping problem. Any questions? I hope some of you did it this way. Okay. Okay, so I will not. So you can cross check with counter normalize, right? If you look at only the 5 rows, you actually just have probability of a is equal to t. A is equal to taking the value of truth is just 2 by 5, and that was what counter normalize was step we were doing, right? So counter normalizing and MLE is the same for directed probabilistic graphical models. Okay, and we can repeat these steps for the other 2 parameters or parameter sets. It happens that theta 2 MLE is actually a 2-dimensional parameter. Okay, it will have 2 parameters because I think theta 2 corresponds to probability of B given A. So A can take two values. For each A value, B can take two values. So the total number of parameters in that conditional probability table is 2. Okay. Is that clear? So if we just write this table, right? So A can take two true and false. And so I'm just saying that this will be theta 2 1 and this will be theta 2 2. Let's say this is 1 minus theta 2 1 and this is 1 minus theta 2 2. Right? Is this is a conditional probability table? So you look at this part of the table and this part of the table separately and see that they sum to 1. Right? So there are two parameters, and you can actually just eyeball the table and kind of get the. I mean, you can do counter normalize and just see that it's 1/2 and 2/3 for these two parameters, and for these two parameters it's 1/3 and 0. Is somebody completely lost at this point? Why? I mean, what is the blocking thing? What's the hurdle? I mean, theta 1 is clear, right? It's just the bias of your Bernoulli flip. So let's see. I mean, so let's look at theta 2, right? So it's so theta 2 is the maximizer of that term. So what are those terms? There are 5 terms. What are those 5 terms? Yeah. What are the BI and AI values of the 5 entries in that complete table, right? It's true, true, first row, false, 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 true, false, true. So these are the 5 values, and from here you just want to fill in this table, right? So true, true. So there were 2 entries. Let's do counter normalize because I mean you can do MLE, but you will get the same answer. So these are the 2 entries which correspond to these numbers, and these are the 3 entries which correspond to these numbers, estimates. And so with one true, there's so with true happening 1/2, and this is 1/2 remaining. I mean, is this not clear? 1/2, 1/2. And so for false, you can see that with A being false, B being false only happens once out of 3 observations. And with A being false, B being true happens 2 times out of 3 observations. So the theta 2 2 is 2 by 3. Let's ignore this. Let's focus on just B being true as the, because that's where I've set the parameter, right? So is this computation not evident?
So whenever we'll have to set up the MLE problem, not the expectation maximization, so we'll have to remove all the rows which has any parameters missing.
No, you don't have to. We could have considered the Z1 FT, I guess. Yeah, we could have considered FT as well while estimating this. I mean, it's your choice. I mean, if you have a lot of rows with complete data and only few rows with some entries missing, you can just ignore them. But as I said, there's an extreme case where every row has some entry missing. If you have hundreds of random variables, then you can't delete all of them and do MLE. So you have to do something different. So you can consider the FT row as well, because for AB, for AB you can consider the 6th row, which is TF. Right. So we also for AB, you can't consider others.
For A we can consider, right?
For A you can consider. For A you can consider T. Yeah. For AB you can't consider because there is a missing here as well as missing there.
So for
but for BC you can consider 6 entries.
So for AB, you have to consider only 5. Like B given 8, So we'll remove Z2.
Yeah, because you have missing on 2 rows, right? So, but that is okay. I mean, let's go with the simplistic setting, which is we deleted the entries, and we are doing MLE with complete data. So people who didn't understand that transient, don't worry about it. This is what you can do. Okay. All I'm saying is you count and normalize, and that's how you got. One half for theta to 1 and theta 2 to 2/3. Okay, and similarly you'll have a same type of conditional probability table for BC, and so let's say the first entry would be theta 3 1, that's 1/3, and theta 3 2 would be 0. Okay, that's the solution for the first part of the question. Okay, now for part 2. We have the initial parameters from part 1. Okay, it can be we have these initial parameters from part 1, and so what we will try to do is come up with some estimates for these missing entries. Okay, so to come up with some estimates of these missing entries, so Z1 and Z2 can be either true or false, right? There are only 2 values for each one of them. But I don't know what is the what those missing values are. So for that, I'll try to create 2 objects, Q of Z1 and Q of Z2, which capture the posterior probability of what that location or what that value, the Z1 box or the Z2 box can take given the current parameters. See, with MLE, I estimated all the parameters, which means I know the joint distribution, which means that I can estimate Z1 given the other variables, right? So that's all I'm trying to say. What is the probability that the Z1 box will contain a true given the current parameters? Let the this Q capture that. Okay. So basically that's what I'm saying. So in that, I think for Z1, B was F and C was true. I think the other 2 entries was false and true. Okay. So all I'm trying to ask is, since we already know the model, can you tell me what is the probability that A is equal to true? Can you tell me the probability that A is equal to false, given that evidence for that row? Okay. And similarly for the 7th row, what is the probability that B is true and what is the probability that B is false, given the rest of the other 2 variables, right? So these Qs, so once I compute these are gonna give me the likelihood that that Z1 box had a true or a false. Okay, and so with that I can kind of create a simulated data set, an expanded data set where those entries are filled. Okay, so current values of theta are these. I'm just I guess rewriting them, and we want these conditional distributions. So let's just compute one of them. Just for completeness sake. So probability of A is equal to true given B is equal to false and C is equal to true. Okay, that's just one. So I have the joint distribution with all the parameters, which are these parameters, and I'm asking evaluate a conditional distribution. Okay, so that should be straightforward. So the conditional distribution is just by definition, a joint divided by the right hand side arguments, right? And in fact, it's the right hand side arguments are, if you expand them out, it's just the probability, it's a sum over the variable that is not present, right? So there are 2 arguments remaining. There are 2 values of A is equal to true and A is equal to false. So is the denominator being split into 2 parts clear? It's just the probability of B is equal to B and C is equal to C is just the it's just the sum over all the values that A can take of this thing. A is equal to A, B is equal to B, and C is equal to C. This is what I've written, and A can take 2 values, right? It's just a definition of, I guess this is marginalization, reverse marginalization. So once I have this, I know all these values. I can just read them off because I have the parameters, right? So for example, probability of A true, B false, and C true, which is the numerator, is actually 0 in this case, if you just take those parameters. And Similarly, you can see that if that is true, that is 0, then the A can only take 2 values, right? So if one of the values that you can take is with probability 0, then the other value it will take is going to be with probability 1. Okay, so this one is straightforward. And similarly, the next evaluation is probability of B being true given the other random variable set to specific values, which was that 7th row. Is going to be, again, you can just reuse the parameters in your condition probability tables, and you will again see that this is actually equal to 1. And then 1 minus that would be the probability that B is equal to false, and that's going to be 0. Okay.
So since it has converged after the first, do we need to again iterate again?
Yeah, we'll have to. So now we'll get the following weighted data set. So the Z1 box can be true, Z1 box can be false, and Z2 box can be true or false. And it can happen. So the Q. So we computed these 4 numbers. These are going to be the Q of Z1 equal to true and Q of Z1 equal to false, basically. These are just posterior probabilities, so they are actual distributions. But
If you use the formula, even the second one will come to 0 because you will never transition from.
Yeah, it is 0 and 1, right? So
No, both will come to 0 because
why not?
You're multiplying with it by the probability of C equal to true given B equal to false. In both cases.
I mean, you will get some expanded data set. Maybe the data set is not useful. I don't know, but this is how you would mechanically proceed. I mean, this data set is different from the previous data set that we had, right? 5 rows. Instead of 5 rows, I have since the weight is 0, I have 4 plus 3, 7 rows.
No, I'm not talking about this data set. In terms of computing this data set, in slide 51. Probably.
Sure.
Yeah, so this is when you computed the first probability, you got it as 0.
Yes.
Because it was multiplied by probability of
Yeah.
C.
Yeah.
So now, even in the second version,
Iteration. Second iteration.
No, even in the second.
Yes, that
case
PS.
of A equal to false given B equal to false.
Yeah, we've seen that, right?
No, right below it. Probability of A equal to false given B equal to false, comma C equal to true. Even that will have the same probability which is multiplied, right? And even that
No. I mean, here you have to be consistent, right? Either you choose like this two should sum to 1.
I know, but if you use a formula, it won't come.
I mean, you need to have some consistency. Yeah, I mean, zeros are gonna create some issues, maybe, but here we have, I don't know, we pretty much avoided that by chance. No, I'm just saying that the second number should be 1 because the first number is 0. They have to sum up to 1, right? It's just a probability distribution, so it has to sum up to 1. Yeah. Yeah, you could have gotten the other. Yeah, it's fine. It's fine. Yeah, zeros may cause issues, but now you will hopefully have a changed data set, so maybe you'll move away from 0. I don't know. I have not evaluated it, but you can check. So yeah. So now with this table, now get the thetas again, counter normalize, and again find these Qs, which are basically posterior probabilities of those those random variables taking some value given the evidence. Rest of the observations in that row. Okay, and then you need to get this. This is the solution for that question. Any doubts? Yeah. It's just when you're counting, you just have to count. You can just multiply when you're counting. You increment by 1, right? Instead of incrementing by 1, you increment the weight. That's all. Weighted counting is just that. So whatever the weight values you see, you just count. You just add that weight value. No. So theta 1 would be in this data set. What is the number of times A is true? Okay, you remove that. What is the number of times A is true? 3 times, right? So it's still 1/2. It's 1/2 rather than something else. 2/5. In the previous theta, at the 0th iteration, theta 1 was 2/5. I mean, the way we started it. Now it's huh? No, you remove this, right? This is not there. Weight is 0 and this one is weight is 0. So no, it's yeah, you can count it, whatever. But it could be potentially same, it could be different, whatever. I mean, it's, if you count 0, it doesn't add anything in the numerator and the denominator, right? I mean, so don't worry about so much about the numerical issues, because those are not important. Conceptually, if you're understanding, and even in the exam, you should not focus so much on the numbers, but also reason why you arrive at a number, right? Okay, so I think I'm just flashing the EM algorithm, a slide from 2 lectures ago. So that's what this was. So find the probability of the hidden variable, hidden as in missing variable, for each hidden or missing location, and then you create weighted points, which are basically these QHs, and then compute maximum likelihood or just count and normalize. So that's what we're doing here. Okay, so let's go to Gaussian mixture models. Okay, so okay, let's go through Gaussian mixture models. So we'll try to spend 5 to 10 minutes here. So Gaussian mixture models are again directed probabilistic graphical models. So it's a very simple idea, which is this. Okay, think of having k Gaussian distributions, and let's say z is a component indicator. So think of z as a categorical random variable. Okay, I don't know how many of you have seen multinomial random variable before. Multinomial distribution, right? So multinomial distributions, that random variable is actually just a bunch of counts of different bins, right? So categorical is just an extreme version of that, where the first argument for the multinomial is 1. Okay, so it's basically saying it's an indicator vector. Okay, so instead of saying so in binomial in Bernoulli distribution, either it's heads or tails, right? So you could have represented that as as a random variable which was taking values 1 0 or 0 1. Right? You could have represented it this way, 2 symbols, so this happens with probability whatever p, and this happens with probability 1 minus p. In multinomial, you have maybe 3 coordinates, and so you'll have 1 0 0, 0 1 0, and 0 0 1, and there will be 3 numbers associated with that. So that's a multinomial. It's actually, the proper name is categorical distribution, but it is what it is. So first I think that's what is written. I've written it here. So this is a multinomial distribution, so it will have capital K parameters. If it has K components, then it will have capital K parameters. In fact, one parameter is redundant. It's 1 minus the remaining parameters, right? Just like in a Bernoulli, even though there are 2 outcomes, there's 1 parameter. Now, a multinomial, a categorical distribution is represented in this product form, similar to Bernoulli. In Bernoulli, we said it's theta to the power xi times 1 minus theta to the power 1 minus xi, right? Remember a few minutes ago we did that. So here we are doing whatever is the parameter to the power that coordinate. Okay. Is that product distribution for the multinomial clear, or categorical? Let me just call it categorical because that's the right name. When the first coordinate is 1, it's categorical distribution. Now, Gaussian mixture model defines the probability that x takes some value given this given a realization of z, okay, according to as the sum, okay. So if the realization of z is let's think of mixture model with components k is equal to 2, okay, then either so k is equal to 2, so there is let's focus on the first coordinate. Either the first coordinate is 1 or the first coordinate is 0. right? If the first coordinate is 1, that's called first coordinate 1 is 1 or 2, okay, since there are two components. Apologize. First coordinate is either 1 or 0. So if the first coordinate is 1, then you pick that normal distribution from which you're getting the x, okay? And if the first coordinate is 0, that plays no role, which means that the second coordinate is 1, and you pick the x from that corresponding normal distribution. So if you had two Gaussian distributions, this Gaussian mixture model is saying first you essentially pick which distribution from which you want to generate an x, and from that Gaussian generate an x actually, okay? So that's the definition or the modeling assumption that we're making. The probability of x given z is given this way, okay? And the probability of x itself is going to be similar to this, except that the coefficients are actually the component coefficients, okay? Yeah.
So here in the before step, you're actually doing a sampling there in terms of trying to pick up from two different distributions.
This one?
Or the last before step, P of x given c.
Yeah.
Or yeah, in that.
No, I'm just defining the conditional distribution to be this. See, conditional distribution is with conditional distribution. So x and z are random variables, right? So I'm just saying that the conditional distribution of x given z is that z realizes, right? So z is now not random, and I know that z has k components, okay? Then the conditional distribution of x is just given by a function of z and some other parameters, which are mu and sigma, right? So I know that z is a vector which has k coordinates. Only one of them can be 1, which means that in this sum all the k minus 1 terms are redundant, or one of the terms is from which I am drawing the x from. One of the normal distributions from which I am drawing the x from. It's just a compact way of representing that.
X is nothing but a sample, right? So you're drawing.
Yeah.
For a given class k, you're trying to draw all
Yes.
the x's
Yes.
for a given class k.
Yeah. Yeah, if the class is k, if z realizes that the k coordinate is 1, that means you're just drawing the probability of x is just given by the Gaussian distribution related to the kth component. Yeah. And okay, and the marginal distribution is given in this way, okay? That you can just figure out by just multiplying this and this, okay? Multiplying and marginalizing actually. Now, what is the estimation problem? So we want to focus on EM again, just because this is a version of EM where we are not dealing with discrete, finite random variables anymore. They are not binary. They are not 10 with support of 10 different values. So the estimation problem is going to be find the parameters nu k and sigma k, which maximizes the probability of seeing some data. Okay. Here actually I have not written any data yet. So for a generic data, so this is the probability of seeing a generic data point x, and I'm asking what are the parameters which maximize the probability of seeing a generic data point x. Okay. So this is very similar to the hidden variable directed probabilistic graphical model example that we saw. Okay, where G was not observed. So this was the type of data, so we couldn't even observe G, and we were trying to learn the parameters of this graphical model, which means that we were learning the conditional distribution of R given G, because we were assuming parameter sharing, and the probability of G itself, right? So whatever the parameters for probability of G were, and parameters for R given G, and this is very similar to that in the sense we are only observing X, and we are assuming the existence of another random variable G. Another random variable Z, right? So we have to learn. So although we are only interested in learning the parameters of the k components, actually not just this. So although we observe only X, we have to deal with this hidden variable Z, right? So the hidden variable Z's parameters would be pi k, because you see probability of Z is determined by these pi k scalars, right? So let's look at this. So Z is, as I said, is a k-dimensional vector with all zeros except for one of the coordinates being 1. That's how the random variable realizes, right? So that's this set is just showing what are the possible values of Z that the Z vector can take. It's every coordinate is going to be 0 or 1, and the sum over all coordinates is going to be 1. It's a very succinct way of saying that only one of the entries is going to be 0, one of the entries is going to be 1, and everything else is going to be 0. Okay. And probability of x. So in the previous slide, I wrote probability of x is equal to something, right? So I'm just doing that here. Actually marginalizing over z, and you can see that probability of x comma z. Probability of x comma z is going to be actually this quantity, the joint probability of x and a z value. Okay, you can see that. So one of the coordinates is going to be so zk can take only values 0 or 1 out of the k coordinates. So many of the terms will be actually to the power 0, so they are ones, and one of the term is going to be remaining, right? So okay. Nice. Okay, for now let's assume that this is the joint distribution. Let's assume that this is a marginal distribution. Okay, and move forward. So since the expression of the marginal distribution is like this, it involves the unknown parameter pi k, because z is a random variable which I have not seen, right? I have not observed, it's not in my data. I have only seen a bunch of x's, x1 to let's say some number of data points, xn, right? With those data points, I'm trying to learn the parameters of this joint distribution, right? That's the maximum likelihood estimation problem. So the marginal log likelihood, which is this, over my observed data, because x superscript I is my sample, so I'm observing a bunch of such data points. So that's going to be my log likelihood. With what is the parameter? The parameter is going to be all the k components of my multinomial or the categorical distribution, and the k means and the k variances that determine each of the components Gaussian distribution, right? So those are the parameters. So these are the, so I need to maximize over theta of this log likelihood, okay, over my training data. That's the usual MLE procedure. So it's not clear how to do this. Figure out the theta which maximizes this number, okay, like we saw in Bernoulli and a lot of other cases. So I'm just contrasting it by a different objective. Let's say if our objective was to actually, let's say we had z's, in the sense we were not just observing xi's, x superscript i's, which were the samples. We were also observing from which component they came from. Okay, that was the hidden variable. Let's assume we have the hidden variable. It's not no more hidden. Then our objective likelihood term would be just the same thing, except instead of this marginal or marginal distribution, it will be the joint distribution, right? And the joint distribution, I've written it here. It's a product, right? So that just if you take the log, it's going to be z. Z log this plus z log z log pi k. Okay, it's just the logarithm of this quantity here. Okay. So this term is nice because I have observed z's and I have observed i's. So, and one set of parameters, the means and the variances only affect this term, and pi k only affects this term. So I could have done something similar to what I was doing earlier. Yeah.
I have a doubt in the first point here. So if you're saying that the z is not observed, right?
Yeah, if z is not observed, then we only care about maximizing the likelihood of the data.
But in the before slide, you actually said that when the z realizes, you actually would be able to find the probability.
That's the generative process by which we are thinking the data is getting generated. So although you observe data which is just x's, in the Gaussian mixture model, we are thinking that okay, let's realize a categorical random variable z, and then pick one of the Gaussian distributions and then get the x. So that's a generative view of how the data might have been generated. That's the modeling assumption, but we only get to observe x's. Okay. From the x's, now we need to reverse engineer and figure out the pi's and the means and the variances. Okay. Yeah, so the complete log likelihood as a simpler form. So, so basically, if what I'm trying to say is that if we know the hidden variables, in the sense they were observed, then we just counter normalize whatever we were doing before, or at least not exactly counter normalize, but we have two terms and now we can, for each term we can maximize over the means and variance, maximize over pi's. Okay. Second point is if we knew theta, then we can find the best zi, since we can compute the posterior of zi given data. So it's very similar to the previous example, where if we have all these parameters, then given x, I can tell you what is the most likely component from which it came from. It's just the posterior probability, right? If I know the joint, full parameterization of the joint, I can find the conditional distribution of z equal to the first component, second component, and so on, given x, right? And in fact, that's what I've written here. So probability of zk is equal to 1. So I, this is the sample. So let's say for ith sample, zk is equal to kth component is equal to 1. It's just the kth component's probability mass divided by all components' probability mass. Okay, that's just you can check that this is the conditional distribution. We are not going to evaluate that, but so also we want to solve this problem because this problem is easy when we observe z's, and not this problem when we don't observe z's. When we don't observe z's, it's as we want to solve the problem where we don't observe z's versus a problem where we observe z's. Okay. So this is just think of it as when we're marginalizing over z's, we only get probabilities of x's, and that was the original maximum likelihood when we only observe some data and we want to maximize the parameters given data. Now, very similar to the intuition that we had in the directed probabilistic graphical model case, in the discrete case, we were trying to find the probability of the missing values, hidden values, given the current parameters, right? So given the current parameter, I was estimating q of z1, z2 in the previous example, right? Similarly, here we are going to try to estimate the probability that z takes some value given the current parameters and the current xi. Okay, so we are basically we are filling the missing values of z superscript I. For every observation, we have xi, x superscript I, but we don't have the corresponding z superscript I. But let's say we started from a parameter set, then we can fill in the probability that z superscript I took some value, right, given xi and the parameters, which was what we were doing in even the previous example. So let's look at the log of the probability of x given theta. This is a marginal distribution. Okay, theta is the set of pi's, means, and variances. Okay, if you just so p of x comma theta is the probability of the joint marginalized over the z's which are not observed. Okay, now I'm going to introduce multiply and divide by an object q. Okay, it's a function of z. Okay, so it's going to be a k-dimensional vector, let's say. In fact, we'll make it a distribution, and you'll see that it is actually the posterior distribution of z's given x's. But let's multiply and divide. Okay, and we can push the log inside, okay, and have an inequality. And we are not going to go through how we can push the log inside. It's called Jensen's inequality, but doesn't matter. From this equation, which was just equality, which was just the log of the marginal, we are going to get a lower bound, which looks like this. Okay, and the lower bound can be reformulated in some expression, but it doesn't matter. So let's just call this lower bound L of q comma theta, because it depends on q and it depends on theta. Okay, it depends on two interesting things. X and Z are sorry, Z is anyway getting marginalized away. So let's explicitly denote it as a function of Q and theta. Yeah. So what are we trying to show here? So here we had the log of the probability of the marginal, and we lower bounded it with some quantity, which is a function of Q and theta. Okay. I mean, it's a function of Q and theta as well as X actually. So we lower bounded it. Now we can show that when Q takes a specific value, which is the posterior distribution of Z given X and the current parameters, which is what I was talking about, then this lower bound actually touches that, is equal to the log of the probability of X given theta. In the sense, this lower bound is tight when Q takes a specific value. Okay. Is that somewhat making sense? So we have this marginal distribution. We somehow lower bounded it by introducing a factor Q, and we are saying that if Q takes a specific value, then the lower bound is actually tight. There is no inequality there. Okay. So what are we trying to do? So we have the log of probability of X given theta. Okay. So let's say we have some theta, some set of parameters, some pi's, some means, some variances. In one dimension, let's say there's going to be a scalar mean, and variance is going to be again a scalar. Okay, and let's say with those parameters, let's say the Gaussian mixture models this distribution. Okay, marginal distribution. Why does the marginal distribution look like that? Maybe there's a bunch of Gaussians like this, like this, like this. Then the marginal distribution with the mixture model would look like this, right? Because it's the sum of a bunch of mixtures, bunch of components which are Gaussian. Similarly, the curve over there is trying to kind of depict that this is a mixture model, so it has, some number of peaks. Okay. Now this L of Q comma theta. So theta is the same thing as there, and I can draw this for different values of Q actually. So for a fixed value for a particular value of Q, this curve touches this distribution. This above curve. Okay. Actually, one incorrect statement I made. Let's scratch this. So this is fine. This is a mixture model. But actually, what I'm plotting here is not a function of X. It's a function of theta. So think of the log of probability of X given theta as a function of theta. So fix an X, okay, fix an arbitrary X, then you can find the probability of X given theta for every parameter, right? Are you guys following? So this is a function of X and theta, right? That much is kind of clear, right? So let's fix an X, okay, and think of this as a function of theta, right? Now I'm drawing this curve as a function of theta. It's just a diagrammatic thing because theta is actually multiple dimensions. There's means and variances and so on. So this is a function of theta. It looks like this. Let's say what I'm saying is that L of Q comma theta for various values of Q would look like this. Okay. In a sense, it will touch at some point with the original curve when Q is equal to some value, some fixed value. And what we are trying to do is, since we lower bounded this as a lower bound for this, we can, for a given theta, we can find a Q where it touches, and then use that Q to update my theta value. So we can move from one theta to another in this way. So let's go to the EM algorithm to kind of understand what's happening. It's actually very similar to what we've been seeing so far. So let's start with some parameter set theta naught, okay. And the expectation step in this Gaussian mixture model is going to be very similar to what we did in the discrete case. Q of Z is going to be probability of the hidden given the given the observed and the current parameter and the previous parameter in this case. Okay. This is what we were doing even for DPGMs or even the discrete versions. Okay, so this is the same as before, and the maximization step is going to be instead of doing an MLE that we were doing in the discrete case, we are going to since we got a Q, we have now gotten the complete data just as before. Now we're going to solve the likelihood problem where we have the completed data. So we are assuming Z's exist and Z's are distributed according to Q, and that's why there's an expectation of Q. Okay, it's like, just like the count and normalize, where if let's say Q was 0.3 and 0.7, you would while counting you would take those weights, right? So that weighting is actually an expectation. So that's the maximization step. So same as before, but with continuous random variables. Okay. So I'll skip the explicit expression for the Q function, but given a bunch of parameters, the Q function is just a ratio of two terms. When you already have the parameters mu, sigmas, and pi's, you can compute Q. Okay, for each coordinate of the multinomial distribution, and given Q. Okay, let me skip this. And given Q, you can compute some new bunch of parameters, and that's going to be again that maximization is actually again something similar to count and normalize with weights. Okay, so what I'm trying to show is an analogy between the discrete random variable case and the continuous random variable case. So in the maximization step, which is count and normalize, again you have weighted counting or normalizing for the means and the variances. I mean, you can see that this is just weighted mean computation, weighted variance computation. So that's the end of Gaussian mixture models and EM. Okay, when you don't observe one full the hidden random variable, which is the component selector. Okay, so given that, so let's so the topics related to PGMs are these. Which you can, I think we've gone through quite a bit in detail about these topics, so it should be fine. Any questions at this point? Yeah.
So, I have a doubt on the
Yeah.
So here, can you go to the graph?
Yeah.
So here, basically what you are trying to find a Q such that, basically you're finding a Q such that the beta actually catches the margin.
I mean, we know which Q at what Q. We are not finding the Q. I mean, this pictorial diagram is just showing we are. So EM has to do. So EM is an algorithm where we are trying to. Is an algorithm where we are still trying to find the best parameters, right? The pi's, in this case, the means and the variances, right? So we want to show that we are making progress. We are converging to a local optima, and so this graph is just a illustrative graph where, because first of all theta is not one dimensional, it's just showing that Q of z you can just evaluate by previous theta value. Okay, but when you substitute the when you use that Q of z and get the next value, you will make progress either this way or this way, whichever some direction where there is a local optima. So here, for example, there's a local optima with respect to theta here, or there's a local optima here, there's a local optima here, there. Yeah, so theta nu is actually this this one. Okay, so Q is just deterministic. There is no optimization happening there. We know that at this Q it does touch. Okay, at theta old at this Q it touches. I'm going to use that Q in the next. I'm going to use that Q and find another theta, and that theta is going to be higher.
And that the Z right now is no longer considered to be great. So it is kind of realized as you go on.
Yeah, because I know Q of z, I think with probability. So when we say Q of z, then z is taking some value. Since it's a categorical distribution, z is taking a value. Let's say 0, 1 with probability p, and 0, 1, 0 with probability. Sorry, 1, 0 with probability p, and 0, 1 with probability 1 minus q is captured. And so those are like the weights. That's why we have an expectation. So we are assuming z is realized. Just like in the table case, we were saying there's a weight for the missing z1 and z2 boxes, right? Similarly, it's the same thing happening here. Okay, so as I was saying, these are some topics that you need to be familiar with. So we will skip the two other reviews. Online machine learning, and so deep learning, really there was not much to review because it's been mostly computational, so we're gonna focus only on the classification pipeline and stuff like that. So let me just list down the topics for online learning. Where is it? Yeah, so this is what we saw. So these are the key topics. Basically, understanding what is A/B testing, what is the online learning setting, what is the stochastic version, non-stochastic version, and we saw, at least in in terms of examples, what was the full information case and what is the binary information case. We also saw a full information algorithm called EXP, and we also saw multi-unbanded algorithm called EXP3 and a contextual banded algorithm called EXP4. So just be familiar with how they actually run in terms of procedure. Okay, it's not about how well the algorithm does in terms of analysis. We haven't looked at analysis, but we have looked at how the algorithm runs in each round, right? How does it make use of previous data to move forward, take the next action, right? So that needs to be clear. And finally, for the topics for the deep learning part are actually not very complex. So basically, try to understand each of the 4 parts of the classification pipeline we discussed in the first lecture, the role of regularization, and like graph propagation that you have solved, I think in assignment 1's first question, and so on. In CNN, just understand what is what is the convolution layer doing, what's the pooling layer doing, and there were a few other small things, but major. So most importantly, just understand what is the convolution layer doing and the pooling layer doing. RNNs, just understand how the structure looks like, but it's not very important. And in terms of data domains, mostly what are these nice embeddings for words, because that's a very nice interpretation, nice view. So you should be knowing about embeddings. So any questions at this point about the exam? Format of the exam?
What kind of
So it's about 150 minutes, right? So about 15 questions. 1-5. I mean, some true and false, and some questions like basically stepping through things. Right here, we have not really analyzed each of the techniques in full depth. So it's mostly just going to be, do you understand the high-level idea of what's happening, and can you step through few iterations of something? That's what I think even in the assignment you did, right? Okay. One second. So percentage of each topic, it's going to be 1/3. Or maybe I don't know. 1/6 for the last, and then 1/2 of 5/6 of the remaining. Yeah.
Can you bring both CVs?
No, one should be enough. Yeah. Yeah. Let's go ahead. No, it will be applied. Basically, numbers. So theoretical in the sense that, for example, one of the examples in this lecture slides is proving something, but there it's not like you have to prove something. I mean, we won't give you a statement and ask you to prove stuff. We'll say this statement requires some algebra, so can you at least can you do the algebra? So that will be like you have a less than equal to b. Can you show that? That you can just easily show. I mean, you can have a look at the example and see how it looks like. Yeah.
Is Gaussian mixture model something?
No. If it is going to be there, then we will give you sufficient detail so you don't have to do anything. I mean, you don't have to remember stuff. Okay. Do you have any question or? They'll be what? No, I mean it will be small scale calculations. Actually, the precision of the calculation doesn't matter. Okay. It's 1/6 5 by 12 5 by 12. Is that? Oh no, 2/6 5 by 12. No. Huh? Yeah, sorry, I know. Yeah.
Is it possible for me to schedule office hours with you on Friday?
Tomorrow?
Friday. Thursday is it, but Thursday I may not be able to.
Why Friday?
Or Saturday or Monday. Sorry, not Saturday. Monday.
Yeah, Monday and all fine.
I mean, sometime.
You don't have to schedule. Okay.
In the sense that